So this next unit is a short unit. It's only 4 sections and we don't spend very long on any one section. But all of this is important stuff to have you ready for the next unit, actually the next 2 units, which are on series. And that's one of the big differences between AB and BC is that BC spends a good bit of time doing series. Fact is, everything we do from this point to the end of, I'll say the end of the year, but till the end of where we're learning new material, it's all BC only material. It's not stuff that they'll do in AB. So today we're going to talk specifically about sequences. And the ideas are, I think, pretty straightforward. And I don't know how much you did with sequences in pre-cal.
I think we did a little bit in pre-cal.
So you're at least familiar with it some. So again, I'll try not to insult anyone's intelligence going over this, but if you've forgotten it or you haven't seen it in a while, we'll knock the cobwebs off. So a sequence, which is written with the curly brackets of A sub n, is just a list of numbers written in an explicit order. Explicit meaning it is specified. There's only one order for this sequence. So if, for example, A sub 7 is equal to 18, that means that the 7th term of the sequence is 18. So the subscript tells you which number it is in the sequence, and then the 18 tells you the value of that term. Okay? There are 2 kinds that we're going to look at today specifically. The first one is an arithmetic sequence. And an arithmetic sequence, A sub n, is a sequence in which A sub n is equal to A plus n minus 1 times d. And that's if you're writing it explicitly. Or A sub 1 is equal to A, and A sub n is equal to A sub n minus 1, meaning the previous term, plus d. Where A and D are both constants, and D is called the common difference. I want you to look at this and then look at do you see that they're really the same? Right? So people are like, well, why did we bother talking about sequences at all then? Here's the difference between those two. I mean, the things that are the same, it gives you a starting value. It gives you where you're starting. Here, we're starting we're starting with n is 1, so we're going to start at 0. This tells you we're going to start somewhere different than x1. And then this tells you how much you go up or down each time. That's the common difference. Okay? What's the difference between them? The difference between them is that if we were to graph this, this is the entire line, right? If we graph this, this is a whole bunch of unconnected points that are along some line, right? We say that this is continuous and this is what's called discrete. Discrete means you just have a value and then you have another value and you have another value, okay? So you need to be able to write a sequence in explicit and recursive format. So if we have this sequence, so we know the value of the first term, and we can pretty quickly figure out, well, what is the common difference? The common difference is a positive 4. So you're like, okie dokie. So the first term is A. So I'm going to write, all right, A sub n is equal to the first term, negative 5, plus, and I don't mind if you write it first so that it's more like point slope form. And again, this is one of the many reasons why I greatly prefer point slope form to slope intercept form, because it leads to some things in calculus. So that's the explicit. Your book will probably, and I don't remember, I apologize, but probably do what most algebra textbooks do. You know how yours, when you were giving the equation of a tangent line, how it always would change it into slope-intercept form, right? Which I'm like, why? Why would you bother to do that? I don't remember, your book probably does the same thing here. Distributing the 4, and then they say a sub n is equal to -9 plus 4n. My problem with that is then it obscures the fact that this is starting at -5. This makes you think, oh, it's starting at -9, but there is no zero term. There's only the first term. You substitute 1 into this, you get -5. That's where it starts. Okay? N is always a positive integer. That's why when I drew this over here, I started at about x equals 1. All right, and then a recursive rule. So the recursive rule, you start off by saying, all right, a sub 1 is equal to -5. And a sub n is equal to the previous term, a sub n minus 1, plus 4, because that's how much we're adding on each time. It's just two different ways to write the sequence. Did y'all do sequence writing at all, or?
Yeah, I think a little bit.
Okay. Now, another kind that's actually for long term, what we're going to do is more important is a geometric sequence. Is this not at the bottom of your page? It's like, why is everybody turning pages?
Yeah.
All right, so a geometric sequence, a sub n, is a sequence in which a sub n is equal to a times r to the n minus 1 explicitly, or a sub 1 is equal to a, and a sub n is equal to a sub n minus 1, the previous term, times r, for n greater than or equal to 2. Now notice this specifies that for the recursive, you have to include this part that n is greater than or equal to 2. You don't have to in the other one, because if we go back to this, we know the first term, right? So it's okay that we don't have, we could say the first term was equal to the previous term. Well, there actually is no previous term. So this should probably include that n is greater than or equal to 1, but we usually don't bother. We usually say n are what are called the natural numbers, 1, 2, 3, 4, 5, etc., etc. Anyway, this is a lot like y is equal to k times b to the x power. This is exponential growth, or decay if b happens to be negative. Right? You've done a lot of things with that, right? Exponential functions. So here, for the geometric sequence, 3, -6, 12, -24, write both an explicit and a recursive rule. The explicit rule would be a sub n is equal to the first term, 3, times, what's the common ratio here? In other words, if I take one term and divide it by the previous term, you get that that's -2. So it's -2 raised to the n minus 1 power. And then if we want to do it recursively, we say that a sub 1 is equal to 3, and a sub n is going to be equal to, I usually write the common ratio out in front, -2 times a sub n minus 1. It's -2 times the previous term. By the way, we talked about when this is growth and when this is decay. What happens in an exponential if the base is a number between 0 and 1? So yeah, it decays, but really, really, really slowly, right? And it gets close to 0. Okay? So we have decay when this is between 0 and 1. If it's bigger than 1, then we have growth. Okay? That's going to become important to us a little bit later on as well. All right, one of the problems, I can remember doing this, and it was probably Algebra 2, but it may have been pre-cal. I remember doing these problems in high school. I don't know why I remember these in particular. I don't remember much of those specifically, but it says here, the second and fifth terms of a geometric sequence are 6 and negative 48 respectively. Find an explicit rule for the nth term. I always went, okay, so that's the first term, the second term, the third, the fourth, and then the fifth term was negative 48. So I need to multiply 6 times something to get this term, times something to get this next term, times that same something to get this term. So this is going to be, you don't have to write this, but that'll be 6 times r. And this will be 6 times r squared, right? Because you're multiplying by r each time. So 48 is 6r cubed. So if 6r cubed is equal to 48, dividing by 6, negative 48, we get negative 8. Taking the cube root, we get r is negative 2. So now if I'm going the opposite direction, this is going to be 6 over r. So this is going to be 6 over negative 2. This is negative 3. So I don't need to know these two terms to be able to write the explicit rule. It's going to be a sub n is equal to negative 2, negative 3 times negative 2 to the n minus 1 power. And you can see why it's n minus 1 there, because if n is 1, we want the first term. We want the negative 3. We want this part to drop out. Okay? All right. One of the things we have to talk about is the limit of a sequence. And the idea is actually pretty straightforward. If f of x is equal to a sub n, for all x equal to n greater than or equal to 1, so that function would go through all of the points on our sequence if we were to plot all those points. Then, if the limit as x approaches infinity of f of x is equal to L, then the limit as n approaches infinity of a sub n is equal to L, and we say that the sequence a sub n, converges to L. In other words, that's the value that it eventually approaches. If, on the other hand, the limit as x goes to infinity of f of x is equal to plus or minus infinity, or fails to exist in some other way, and we'll talk about that in a second with an example, then the sequence a sub n diverges. So, if we're determining the convergence or divergence of this sequence, what we're going to do is we're going to look at the limit as x goes to infinity of 2x minus 1 over x. Hopefully that's one that you can just look at and go, oh yeah, I know what that is. Nope. Okay, well, let's do a couple of values, and I think you're gonna kind of see. All right, so if x was 1, that'd be 2 minus 1 is 1 over 2 is a half. And if x is 2, that's 4 minus 1 is 3 over 2. And then it's going to be, when it's 3, that's 6 minus 1 is 5. Oh, sorry, this was supposed to be 1 over 2, that's over 3. When we're at, if x were 4, this would be 8 minus 1 over 4, so that's 7 over 4. So you can see these are going up by 2 each time. These are going up by 1 each time, right? So 9/5, 11/6, 13/7. What are these getting really close to already? 2. And think about it. As x goes to infinity, I always talk about when you're looking at rational functions where you have a function over another function, as x gets big, how much does this -1 matter? Almost not at all. So 2x is the dominant term as x approaches infinity. And in the denominator, we only have one term. And then 2x over x is equal to what? 2. That's kind of the way I approach that. I always look at the dominant terms. If it's a polynomial, the dominant term as x goes to infinity, or negative infinity for that matter, is always going to be the term with the highest power. All right, so since this goes to 2, then my sequence a sub n converges to 2. And I'm always careful to write that this sequence converges to 2. Why? Because in a very little while we'll also have series, and we'll talk about whether series converge or diverge. It's important that you have them distinct. It's, for me at least, because of the way my brain categorizes things, it's unfortunate that these two words start with the same two letters. I frequently will say sequence when I mean series and series when I mean sequence. But it's really important that you keep the two separate as much as you can in your head. Okay? All right. So let's look at this one. So we'll look at, well, what is the limit as n goes to infinity, or excuse me, as x goes to infinity, of -1 to the x times x minus 1 over x. As x goes to infinity, what is x minus 1 over x going to go to? 1. So this part's going to go to 1. What's going to happen to the first part, though, the -1 to the x? As you're increasing, and we're only, think about just doing whole numbers for a moment, 5, then 6, then 7, then 8, then 9, then 10, et cetera, et cetera. What's going to happen with this? Yeah, it's going to alternate between -1 and +1, right? So times something that's getting close to 1. So near the end, not there is no end, but as I get bigger and bigger, my values are going to be really close to +1, then -1, then +1, then -1. So does this limit exist? No. So this limit does not exist. Therefore, the sequence a sub n is said to diverge, because it doesn't settle down to a particular value. To converge, It has to settle down to be getting really close to a particular value. All right, so let's take a look at this one. This one they've written in recursive form. And I'm like, okay, why are you bothering to write this in recursive form? It's to make you have to rewrite it in explicit form. So this is I'm going to pause for just a second. I have a call from a doctor that I have to take. Hello? I hate doctor's offices that are like, call us and we'll call you back. I'm like, are you going to call me at a convenient time? Probably not. All right. So this is an arithmetic sequence. And so we know that it's starting at 4 and the common difference is 3. So this is 4 plus 3 times n minus 1. So rewriting it as an explicit form rather than recursive form is helpful. And then we'll do, all right, well, what is the limit as x goes to infinity of 4 minus 3 times x minus 1? And what is that? Not quite. It's negative infinity. Because you're... why did I write a minus sign? Sorry. This should be positive. I don't know why I suddenly switched that to a negative sign there. So remember, when you say that the limit is infinity, you're saying the limit doesn't exist, right? But you're explaining why it doesn't exist. So my sequence a sub n diverges. It's never going to settle down to a particular value. Every time you get one value, you're going to add 3 to get to the next one. So never settles down to a particular value. All right. Page 3. So the sandwich theorem, we did that earlier in the year, way earlier in the year when we were doing limits. And you can also apply the same sort of idea to sequences. So it says that if the limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of c sub n, and those are both equal to some L, where L is some constant. And if there's an integer capital N, so that when little n is greater than capital N, a sub n is less than or equal to b sub n is less than or equal to c sub n. So either equal to or in between the two, then the limit as n goes to infinity of b sub n is equal to L. You're like, okay, that's an awful lot, but basically what's happening is this. As you go to infinity, what has to happen is that these both have to go to some particular value. So if a sub n is up here and it eventually gets closer and closer to L, and then c sub n is maybe down here. Oh, I have it the other way around, so I'll make this c sub n, and this is your b sub n, a sub n, excuse me, and b sub n is in between those two. It gets squeezed between the two, okay? Which can be helpful for showing things like this. Show that the sequence, the sine of n over n, converges, and find its limit. Okay, so we did exactly the same thing earlier in the year. What does sine of n oscillate between? -1 and 1. So we know that -1 over n is less than or equal to sine of n over n, which is less than or equal to 1 over n. And we know that the limit as n goes to infinity of -1 over n is going to be what? 0. And the limit as n goes to infinity of 1 over n is likewise 0. So this is sandwiched in between them. So that means that the limit as n goes to infinity of sine of n over n is equal to 0. And we say that the sequence sine of n over n converges to 0. We're going to use this idea quite a lot when we get to series. Now, it's important in its own right for this unit, but when we get to series, the first thing you always do is you look at a sequence of numbers and you say, does that sequence of numbers converge or diverge? And that's going to tell you a lot about the series. Okay? If that makes sense. Don't worry about, you're like, well, why are we going to look at that? We'll talk about that later. But it's the first step when you're looking at a series is pretty much always to look at the sequence that's associated with it and find out whether it converges or diverges. And if it converges, what does it converge to? You got to be really good at this. And I think you'll get really good at this pretty quick. Okay? All right. That's it for the lesson.